Now I'm going to talk about some simple propositions. Let's talk about proposition number 1. Suppose E is a member of S. E is a subset of S. If here is, and S is a sample space. If that's the sample space, E is in it. E is in it. So this is E. And this is not E. This is not E. Clearly, E union not E, that is E union E complement, is S. Okay, first I'll say that E and not E, or E complement, are always mutually exclusive. By definition, they have nothing in common. Whatever E has, E complement is everything else. They never have anything in common. By definition, E complement is everything but E. E complement is the sample space, take away E. It's everything but E. So now, I want to prove something. I want to prove that the probability of E plus the probability of not E is 1. E complement. Okay, and one way of seeing it is it makes up the sample space. E union E complement is the sample space. The sample space is E union E complement. Okay, the sample space, I don't know why this didn't come out. The sample space is E union E complement. Therefore, the probability of S is equal to the probability of E plus the probability of E complement. Now, some people, some textbooks, they put a dot above the U to say that what you're taking the union of are mutually exclusive. That's why I was able to separate them by an earlier axiom. But P of S is 1. So P of S equals 1, and P of S equals this. That is 1 equals this by transitive property of equality. 1 equals P of E plus P of E complement. Okay, the important thing here is if you take away P of E from both sides, if you take away the probability of E from both sides, on the left side, you get 1 minus the probability of E, and on the right side, you just get the probability of E complement. That's a new way of calculating the probability of the complement. For example, if the probability that it rains tomorrow is 0.3, well then the probability that it doesn't rain tomorrow is 1 minus the probability that it rains, and we know, or where it's given, the probability that it rains is 0.3. And our final answer is 0.7, which is a reasonable answer because it's between 0 and 1. The probability of any event is always between 0 and 1. Okay, that's a nice way of finding the complements. If you know the probability of E is 0.4, then the probability of E complement is 1 minus 0.4, 0.6. Now, the next proposition, proposition number 2, says if E is a subset of F, then the probability of E is less than or equal to the probability of F. It can't be more. If this is F and E is in here. Now, it could have been that this is F and the same thing as E. It could be that F and E are equal. That symbol allows equality. It could be equal. Some books will actually put an equal sign. It could be one of those two. Well, if it's the first one, this one here, imagine you're throwing a dot at this board. Well, the probability that you land in F is going to be bigger than the probability that you land in E. So it does make sense that the probability of E happening is less than the probability that F happens. Or maybe they're equal. E could have been you throw a die and you get a 1, 2, or 3. F, which includes E, could have been you get a 1, 2, 3, or you get a 4 and a 5. And, of course, 6 would be outside. Now, inside F, there's no reason you need to see... Oops. Let's try that again. There's no reason to see that circle inside of F. For example, if this is the sample space, that is, and the sample space is the result of tossing one die. Everything in here is the result of tossing one die. Here is F. It has 4, 5, 1, 2, and 3, and it doesn't have 6. But it turns out that that's called set E. Within F is 1, 2, 3, 4, 5. There's no reason when you're looking inside F to see a circle around the 1, 2, and the 3. The probability of rolling a 1, 2, or 3 is going to be less than the probability of rolling a 1, 2, 3, 4, or 5. I can stick in the equal sign right here if I like. This makes a lot of sense. Now, as an advanced student, one taking probability theory, having finished Calc 3 and all, you really should know how to prove this. If you don't want to know how to prove this, cool. Fast forward their video. But for completeness, I'm going to prove this. Now, so let's write proof. You prove propositions. F is E. So again, here's E. Sorry, here's F. And inside is E. So you have E, and then you add on this stuff. You add on this stuff. Well, it's in F, and it's not in C. We have that. And they're mutually exclusive, because to be in F and E complement, you have to be in E complement. You may not be everything in E complement, but you have to be in E complement. Why might you not be everything in E complement? Because E complement is everything outside of E. But some of that's not in F. For example, the parts that I am attempting to erase, they're not in F. They're not in F. Okay. So what we can now say is the probability of F is equal to the probability of this. But since these two sets are disjoint, I can take the probabilities separately and add them. The probability of E plus the probability of F and E complement. Now, this is some event, and we're taking the probability of it. So it must be using one of our axioms. Let's use it completely. Since the probability of F intersect E complement is bigger than 0, fine, is also less than 1. Less than or equal to 1. Since this part is 0 or positive. Now, if this piece is 0, P of E plus 0 is just P of E. And then we get that P of F equals P of E. P of F equals P of E. Now, if this part is positive, like 0.1, well then, this has to be less than P of F, because P of F is this plus 0.1. If P of F is, so let me just write it down here for a moment. P of F, not P of E, P of F is known to be equal to P of E plus P of F and E complement. Well, if P of F is, say, 0.8, and this here is 0.1, well, this has to be less than 0.8. It's 0.7. P of E is actually bigger than, P of F is actually bigger than P of E. And like I said, it can also be equal. When P of F intersect E complement is 0, then you have equality. So I prove that it's positive. I mean, one is bigger than the other. P of F is at least as big as P of E. If E is in F, then the probability that E happens will be less than or equal to the probability that F happens. Or, rephrasing it, the probability of F is bigger than the probability of E. Bigger than or equal to. Okay, I'm hoping I'm not confusing people by saying this both ways. Of course, there's only one reason why A is less than B, and that's because B is bigger than A. So, if I say that the probability of E is less than the probability of F, there's one reason why the probability of E is less than the probability of F, or equal to. And that's because the probability of F is bigger than or equal to the probability of E. These just go hand in hand. There's only one reason this is less than that, and that's because that's bigger than this, or equal to. Okay, that's the second proposition. The third proposition is very important. It's just going to come up time and time again. Just always going to come up. What is the probability of E union F? here's E, here's F, here's everything. Well, one might say, well, it's the probability of E plus the probability of F. But keep in mind, that's only if E and F are mutually exclusive. See, the probability of E is the chance that you land in here. That's the probability of E. The probability of F is the chance you land in here. Well, yes, if you add those two, you will have covered everything. But there's one minor problem. You covered, or you counted, what was in here 2 times. You counted what was in there twice. You counted it you calculated the probability of E, and you counted it again when you calculated the probability of F. So if you count something 2 times, you only mean to count it 1 time, well, you have to subtract. You have to take away something, to take away a probability. Probability of being in here. But that's the intersection. That's the intersection. That's the intersection. And this is the formula that you need to know. Probability of E union F is the probability of E plus the probability of F minus the probability of that intersection. Now, these are numbers. These are all numbers, and you can move them around. I'm going to move this to the other side, so it becomes plus, because it's minus here. It's going to be plus the probability of E intersect F. I am not going to move this. I am not going to move that. But this one I am going to move. There's no sign in front of it, so it's understood to be positive. When I bring it to the other side, it becomes minus. And here's an alternate form of that formula. What's the chances that you're in the intersection of E and F? It's the probability of E plus the probability of F minus the probability of the union. Now, after this, I'm not going to do as many proofs, but I like this proof. Now, what I did was a geometric proof, a proof using Venn diagrams. But we can prove this being proposition 3, the probability of E union F is the probability of E plus the probability of F minus the probability of E intersect F. Now, if these elements or if these sets are mutually exclusive, if they're mutually exclusive, then this will be 0. And the probability of being in the empty set is 0. And taking away 0 from what I just put a box around doesn't do anything. You just get this. That's what the formula is going to be if the 2 events are mutually exclusive, which, of course, is absolutely not always the case. Okay, it's not always the case that they're mutually exclusive. Okay. Now, how would you prove such a theorem or probability? And the flavor is the same. You want to get mutually exclusive sets that equal E union F. So you have, say, E, you have F, they might intersect, and you have the rest. Well, so it equals U. E union F equals E, I meant to say. But then I have to add that on. And I want them to be mutually exclusive. I only want to add on what's in the dots. Well, what's in the dots is F and not C. These are mutually exclusive. These being this set and this set. This one is clearly in E. It's all of E. And this one is clearly in E complement. That is, it's not in E. Okay, you want to get mutually exclusive sets. Now I can go on to say that the probability of the left side is equal to the probability of the right side. But since the right side, the probability of the left side is equal to the probability of the right side. But since the right side is a union of mutually exclusive sets, I can take the probability of the first set plus the probability of the second set. Now, let us call this equation number 1. Now, I want to do the same thing for F. F, again, you have E, you have F, and you might have things outside of them. F, well, what is F equal? Now, F is in two parts. You have this part, which is in E, and then you have this part of F, which is not in E. And they're disjoint, where I put the slashes and the X's, they're disjoint. That is, F is equal to F and these X's are not in E. You're in F and you're not in E. Or you're in F and you're in E. This comes up a lot. F is broken up into two mutually exclusive parts. The part that has E and the part that doesn't have E. F is broken up into two pieces. The part that is not in F and the part that is in F. These are disjoint. These are disjoint sets, or mutually exclusive sets. These two sets are mutually exclusive. This set and that set. So excuse me a second. This set and that set are mutually exclusive. So the probability of the left side, that is probability of F, is equal to the probability of the right side. But since the probability of the right side is the union of mutually exclusive sets, I can write the probability of the sum. The probability of the first set plus the probability of the second set. And this I'm going to call equation number 2. And I am going to erase this because I need the space. I notice one thing between equation 1 and equation 2. I notice that they both have this. They both have this. So in both of these equations, equation 1 and 2, I'm going to solve for what's in the box. I'm just going to bring the P of E over as minus P of E. So the probability of this, F intersect E complement, is equal to this probability of E union F minus the probability of E. I'm going to do the same thing in the bottom. I'm going to bring this over. So remember, it's plus the probability of the probability of F intersect E, the probability of F intersect E is equal to P of F minus this mess, minus the probability of F intersect E complement. And of course, I didn't do what I meant to do. Sorry about that. I'll show you in a moment what I meant, but let's get rid of this. Like I said at the beginning, they both have this in common. Equation 1 and equation 2. Equation 1 and equation 2 have this in common. So I meant to solve for that in equation 2. The probability of F intersect E complement is equal to P of F, and it is this that I'm bringing over. And since it's plus, when I cross the equal sign, it becomes a minus. Okay. So now, what I'm going to say is, since this and this equal the same exact thing, they both equal P of F intersect E complement, they must equal one another. They must equal one another. And I really need the space, so I'm going to put that up here. They equal one another. If two quantities equal the same thing, they equal one another. Okay, so P of F intersect E complement equals P of E union F minus P of E, and P of F intersect E complement is equal to this, equals to P of F minus P of F intersect E. And just play a little algebra with this, and you'll be okay. Just bring this to the other side. The probability of E intersect F, E union F, equals, when I bring this over, since it's minus, it becomes plus. And of course, for the first term, you don't have to write the plus. You can if you want. And here, this first term doesn't have a sign, so it is plus P of F minus P of F intersect E. Oops, I didn't mean to write C at the very end. But nonetheless, this last statement is exactly what we wanted to show. P of E union F is P of E plus P of F minus P of their intersection. You have to take away the intersection. The harder things you can do, the harder the problems you can do, that means the more easily you can do the easier problems. Hopefully, the ones on your test will be fair. They'll be easy. If you do your work, you understand things, you get them right. All right, so let's do some problems. 2 dice are thrown. A represents the event, the sum is odd. The sum of their 2 dice are odd. Throw 2 dice. B equals at least 1, 1. At least one die is 1. Let's write it that way. At least one die will equal 1. And C is the sum is 5. Well, describe the following. What would A intersect B equal? What would A union be? How would you describe that? How would you describe B intersect C? How would you describe A intersect not B? And how would you describe A intersect B intersect C? Now, in words, remember, intersection, it means and. Union, it means or. So, instead of A, I'm going to say this. Instead of B, I'm going to say that. And instead of intersection, I'll say and. So the sum is odd, and at least one die is 1. So what it could be is 1 and 2, 1 and 4, if I have to get an odd, 1 and 6. Or the second die could have been the 1. I can get at least one die is 1, means one die is 1, could be 1, or both dice can be 1. Well, if they're both 1, that adds up to an even number. 1 plus 1 is 2. So the second one can be 1, and to make it odd, I have to get a 2, or a 4, or a 6. This is exactly how you should describe A intersect B. Now, A or B, that should be B. A or B. The sum is odd, or at least one die is a 1. Well, the sum is odd. You can have 1 with a 2. You can have 1 with the 4. You can have 1 with the 5. I'm just doing A right now. The sum is odd. 1 with the, not a 5. 1 with the 6. Now, you can have a 2 with the 1, or 2 first. Or a 2 with the 3. That adds up to 5. Or a 2 with the 5. You can't have a 2 with the 4. That wouldn't add up to an odd. Or you can have at least one die with the 1. That is, you can also have a 1 with the 2. You can have a 1 with the 3. You can have a 1 with the 4, which I already put. You can have a 1 with the 5, which I didn't put. You can have 1 with the 6, which I did put. Or the 1 can be second. You can have a 1 with the 1. That's where both are 1s. You can have a 2 with the 1. You can have a 3 and then a 1, a 4 and then a 1. The question is, did I make a mistake somewhere? Oops. Let's try this again. Especially if I made a mistake, let's just redo it. You can have the sum is odd. Yeah, I probably didn't make a mistake. And if the sum is odd, you can have a 1 with a 2. You can have a 1. You can't have a 1 with a 3 because that adds up to 4. But you can have 1 with a 4. You can have 1 with a 6. You can also have 2 first. 2 with the 1. 2 with the 3. 2 and 5 is odd, and that's it. You can have 3 with their 2. 3 and 1 are even. 3 plus 2 is odd. You can have 3 with the 4. You can have 3 with their 6. Yeah, I guess I did make a mistake. I didn't do many of these. You can have 4 with the 1. You can have 4 with the 3. You can have 4 with the 5. Then you can have 5 with the 1. That's odd. No, it's not. It's even. You can have 5 with a 2. You can have 5 with a 4. And then you can have 5 with their 6. That's A. Or you can have B. At least one die is a 1. Let's let the first die be a 1. You can have both. You can have 1 with the 1. You can have 1 with the 2, which I already put. You can have 1 with the 3. You can have 1 with the 4, which I have. You can have 1 with the 5, which I don't have. And you can have 1 with the 6. Or the second die can be 1. Well, I did a 1 with the 1. Now I'll do a 2 with the 1, which I already have here, so I don't have to write it. I can do a 3 with the 1. I know I don't have that because that adds up to an even. I can have 4 and then a 1, which I have. I can have 5 and then a 1, which I don't have. And then I can have 6 with the 1, which somehow I didn't do. You can have 6 and a 1. Let me put in the bottom here. This is for A to get odds. You can have 6 with a 3, and you can have 6 with a 5. Okay, so now back to the second entry having a 1. I can have 6 and a 1, and there it is. Minus some silly error. Those are them. Those are all the ones where either the sum is odd or I have 1 or 2 1s. Of course, due to space, say bye to this answer. And same for the first one. So let us try this third one. B and C. B and C. Well, in words, now, just for the record, if on the exam or on a homework problem, if it just says describe, you should say at least one die is a 1. That's for this. And the sum is 5. Okay. But let us describe it in roster form. Let's list their combinations of the, let's list the role of these two dice who have these two properties. The sum is 5, and at least one die is a 1. Well, if the first one is a 1, then I have to get a 4. And that's the only way to get a 5 with a 1 here. If the second one is a 1, then the first one needs to be a 4. And if they're both 1s, that can't be. Because 1 plus 1, it just doesn't add up to 5. So that's the answer to that one. A and not B. A and B complement. Okay. Now, in terms of the number of 1s you can get, when you toss 2 dice, you can get no 1s, you can get exactly 1 1, or you can get exactly 2 1. This is at least 1. But they're saying we don't want at least 1. That means we want 0 1s. We want the sum to be odds and no 1s. Okay, so I'll start with 2. To get odd, you can have 2 and 1, but you can't have a 1. So it's 2 and 3. Just add 2. 2 and 5. If you get a 3 first, 3 and 2 is odd. 3 and 4 is odd. And 3 and 6 is odd. If you get a 4 first, 4 and 1 is odd, but you can't get 1. So 4 and 3, 4 and 5. Those pairs are odd. If you get a 5 first, Add 2, get a 7. Add 4, get a 9. Add 6, get 11, which is odd. You can also get a 6. And due to lack of space, I'll put it up here. You can get a 6 and a 1, that's odd, but you can't get a 1. So 6 and 3, 6 and 5. Actually, if I knew it was just 2 of them, maybe I would have just snuck them in. So here is the answer, and you don't even need this up here. There's the answer in this box. Okay, the last one. They want A, B, and C. You get into the habit of looking at the biggest restriction. That's C. The sum is 5. You want the sum to be odd. You want it to definitely have at least 1, 1, and the sum is 5. Now, you can list this. 1 and 4 is 5, or 2 and, well, let me do it horizontally. 2 and 3 is 5, 3 and 2 is 5, 4 and 1 is 5, and that's it. These are the only pairs whose sum is 5. 1, 4, 2, 3, 3, 2, and 4, 1. Okay. Now, if the sum is 5, which is odd, then the sum is odd. So whenever C is true, A is true. So we definitely satisfied C. I made the sum 5. We definitely satisfied A. The sum is odd. For intersection, we have to satisfy all 3. The middle one says at least one die is a 1. This one doesn't have at least 1, 1. This one doesn't have at least 1, 1. But the first and the last do. That is, the answer to this one is the set that contains 1, 4 and 4, 1. That's the answer. A intersect B intersect C is equal to the set that contains 1, 4 and 4, 1. That's your answer, 100%. Right. Suppose there's 3 people, Abe, Betty, and Carlos, take turns tossing a coin. The first one to get a tail wins. So Abe, Betty, and Carlos each toss a coin. First Abe, then Betty, then Carlos, then Abe, and Betty, and Carlos, and if necessary, Abe, and Betty, and Carlos. They keep going in that order until a tail comes up. So what would the sample space be? Well, it can end just with a tail. If Abe gets a tail, it's done. If Abe gets a head, well, let me not put a comma. If Abe gets a head, and then Betty gets a tail, it's done. Or Abe and Betty get heads, and then Carlos gets the tail. Or they all 3 get a head, 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 and then Abe comes back and wins. Or Abe, Betty, Carlos get a head. It starts again. Abe gets a head. Betty gets a head. Carlos comes and wins. Well, actually wanted Betty to win. If you notice, there's no heads and then her tail. There's one head and then a tail, two heads and then her tail, three heads and then her tail, four heads and then her tail, five heads, A, Betty, Carlos, A, Betty, and then Carlos wins with her tail, etc. It's a series of H's with a T on the end. No H, one H, two H's, three H's, four H's, five H's, then a T at the end. This here would be the sample space. You can't list it because it goes on forever. It might take 29 billion turns or tosses of the coin before somebody wins, or even longer. Is it likely? Of course not. How would you describe that A wins? Well, A can win if if Abe comes and tosses the head, or Abe, Betty, Carlos, and then Abe gets the tail and wins. Or, so this is first round, this is second round. What if Abe wins on the third round? That is, Abe, Betty, Carlos get heads, and then Abe, Betty, Carlos gets a head again, and then Abe gets a head, and then Carlos wins. Oh, no. Abe is going to win. Sorry. Thinking about the last problem. After the first round, nobody wins. After the second round, nobody wins. And then Abe wins. Or, the first winner is in the third round, and it's Abe again. H, nobody won the first round. Another three H's, nobody won the second round. And I made a little mistake in my words. This was the first round, nobody won. This is the second round, nobody won. And Abe won in the third round. Nobody won the first round. Abe won the second round. Abe won the first round. So this is Abe round 1, round 2, round 3, Abe won. Now we go to round 4. That is, nobody wins the first round, nobody wins the second round, nobody wins the third round, and then Abe comes and gets his tail, and he wins, etc. So in other words, it's like the 3 times table. 3 times 0 is 0. 3 times 1 is 3. 3 times 2 is 6. We have no H's and then our tail. That's 3 times 0 is 0. 3 times 1 is 3 heads, then a tail. 3 times 2 is 6 heads, then a tail. Then 3 times 3, 9 heads, and then a tail. It's going to repeat in that fashion. 3, 6, 9. Next time, I'll have 12 H's, and then Abe would win with a tail. What would it mean? What would the sample space look like for Betty to win? The game ends once somebody tosses a tail. And this time, Betty is going to win. The sample, Betty wins. B wins. Well, Betty can win round 1. That is, Abe doesn't win, and then Betty tosses the tail. Or, this is round 1. Or Betty's going to win in round 2. That's round 1. Nobody won. then Abe doesn't win, but Betty does. That's round 2. Now, Betty's going to win in round 3. That is, nobody won the first round. Nobody won the second round. Now the third round. Abe loses. Betty wins. Round 3. Round 4. Betty's going to win in round 4. That is, nobody won the first round, or the second round, or the third round. But Betty's going to win in the upcoming round. Abe loses. Betty wins. Well, how many tails are coming up? Well, now it's the 3 table, but add 1. This is 1. 1 head. 3 times 1 is 3, plus 1 more is 4. 3, and then 1. Where is this 1 coming from? Well, in the round that somebody wins, Abe didn't. There's going to be an H. 3 times 2 is 6. Add 1 is 7. Nobody won round 1. Nobody won round 2. Abe did not win Abe did not win in round 3. But Betty did. Etc. What would the following be? Remember, A means A1, B means B1. Abe wins, Betty wins. What would A union B complement be? What would A union B complement be? Well, here's A, and here's B, and there is person C. A, B, C. You want to put person C on the bottom, go for it. Please, this C here is complement, it's not person C. So this is A. And since this union, I can use the same color marker in the same directions. And this is B. This is B. We don't want that. Well, now somebody's going to win. Somebody's going to win. That is, there's nothing out here. You have to be there. That's where C wins. In fact, if you think about it, there's really no intersection. If this is A, B, and C, for example, this area here means A and C. In here is clearly in A and C. Well, A and C can't win. B and C can't win. A and B can't win. Like I said, B and C can't win. They all 3 can't win. In fact, these are mutually exclusive. If A wins, B didn't win. So you can even do it like this. But the argument I gave in this Venn diagram is perfect. You're not in A union B. You're not in here. So where are you? You're in C. This is A union C. Well, if you're not there, then you must be in C. Okay, so let's just finish this up. What does that mean? Remember, we need to describe the set. And in words, this is the set where C wins. This is the only one we haven't done yet. We let A win, we let B win, now we're letting C win. And please, that C is not Carlos. That C is a complement. It is not Carlos. That is not Carlos. Well, it turns out that it equals Carlos. A union B complement, not A or B. Well, A or B or C wins. Well, it's not A or B. It's not A or B. Then it's C. Okay, what does it mean for C to win? Well, C can win in the first round. Notice C comes last. Say H, H, and then not C, but T for tail, which means you win. This is the first round. Carlos can win the second round, which means nobody won the first round. And then Abe loses, Betty loses, Carlos comes up with the win. Carlos won the second round. Carlos can win the third round. Nobody won the first round. Nobody won the second round. The third round, somebody wins. But it's not Abe, it's not Betty, but it's Carlos. This time, it's not this 3 times table. 3 times are 0, 3 times 1, 3 times 2, 3 times 3, 3 times 4. It's not that. It's always 2 more. 0 plus 2 is 2. Oh, 2 heads and a tail. 3 plus 2 is 5. Yep, 3 heads, and then 2 more is 5. And then the tail. It's always 2 more than the 2 table. 3, 6, and then the 2 loses in the next round. And then the winner. Okay, this completes the section on simple propositions.